All right, today we are going to continue learning about triangle congruence in section 4.4, where we are going to be applying the angle side angle and angle angle side congruence criteria. So adding two more triangle congruence theorems to our toolbox after we learned about side, 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 and side angle side already. And these work in very similar ways. This will be sort of the main four triangle congruence theorems that we will see this chapter. So I bet you can guess with angle side angle congruence what we might write down. But first, I want to show you that angle side angle congruence is truly a congruence theorem. So if I go in here and I go to angle side angle congruence, and I have this little interactive gadget here, and you can see that both of these triangles have a 35-degree angle, a 7-unit side, and a 65-degree angle. And it's showing us that no matter what I try to do with these two lines, if I try to make them longer or shorter, there's only one place where those lines will connect with each other. And therefore, there's only one triangle that has this angle side angle configuration. That means that any triangle that we make with the 35, 7, 65 configuration will be exactly the same, or a congruent triangle. And this would happen with any arrangement of angle, side, and angle. So when we write this, we'll do an if then. So if we have two triangles, and maybe they are triangle A, B, C, and D, E, F, and they have an angle, maybe angle A, right? And then a side that's congruent, maybe AC and DF, and then another angle, maybe angle C and angle F, then I know for sure that triangle ABC is congruent to triangle DEF. We want to make sure that our triangle names are written in the correct order. Notice that with angle angle side, our included side is the one that's congruent. It is included by being in between the two congruent angles, right? If you'll notice the name of this concept and the name of the next one, they both have two angles and one side. It's the order of the angles and the side that are different. In angle angle side, we can bring up the tool again to see what happens if I have two angles and a side like this. So here's two angles, and they have a congruent side that's not in between them. So they have a 43-degree angle, a 57-degree angle, and a congruent side of 11. And if I move back and forth on this point, and I see how many different triangles I can make that will connect, only one triangle will connect with point G. So any time I have an angle side arrangement that's congruent between two triangles, I know that those two triangles have to be congruent. Let's write that down. So I've got angle side congruence, which tells me if I have two triangles, again, we'll do them this way this time, make ourselves a little bit more interesting. And if I say that triangle X, Y, Z is one of the triangles and triangle B, C, D is the other one, I don't know. And if they have angle side congruence, that means that they have two angles, one right after the other, in a congruence fashion, and then one of the other two sides, so either XZ and CB or YZ and DB are congruent to one another. Here we'll put YZ and DB, but it could be that other side, as long as it's not the included side between the two angles, which would make it angle side angle. But if we know this, we can say then triangle, my first one I'll call XYZ, and if I call that first one XYZ, I'm going to need to call the second one CDB. And I know that those two triangles are congruent. Now you might notice that there are some arrangements of triangles that are not on here. We have 4 that are congruence postulates. We also have 2 that are not. The first is angle, angle, angle. Now let's take a look at why angle, angle, angle is not a congruence theorem that we have. So we've got angle, angle, angle for us right here. We've got 3 pairs of congruent angles on these triangles. And what we can do is we can notice that if there are 3 pairs of congruent angles, I can move this triangle without changing its angles. I can make it bigger without changing its angles. So these 2 triangles have exactly the same angles, but they are not congruent. So angle, angle, angle is not a theorem we can use to prove that 2 triangles are congruent. The other one that we don't have that you might have noticed because you're in high school is that we don't have the AS postulate. Angle side side is not a congruence theorem that we can use. Not because it's a swear word, although that helps us to remember that we can't use it, but because when we look at what it will do to our triangles, we say, can we make congruent triangles? Can I make more than one triangle, right? So I have 2 triangles where they have 2 sides next to each other that are congruent, a side of 6 and a side of 11, and then a congruent angle that's 25. If I take this line, I can make a triangle that looks like the one that we started with. But I can keep going with this line, and all of a sudden, hey look, there's another triangle I can make that has the same arrangement of side, side, and angle. So angle, side, side, or side, side, angle will make more than one triangle. We won't always know that triangles with an angle, side, side arrangement will make the same triangle. So they cannot be a congruence postulate either. So those 2, they're not congruence postulates. All right, so let's take a look at some that are. So these are sort of examples that we already took a look at. How many possible triangles can you determine when given 2 angles and the included side? That means our angle, side, angle arrangement. We can only make 1 triangle, which is why it's a congruence, right? It's why it's one of our congruence theorems. And then the question that goes along with this, again, not too difficult. What is the the relationship between triangle AXB and AYB? Well, they've got an angle, a side, and an angle that are congruent to one another, which means that they are congruent by angle, side, angle. So they are congruent by angle, side, angle. Nothing too crazy there because we already kind of took a look at it. Here's the next example. We're using angle, side, angle congruence. So we're going to skip the video, by the way. Don't worry about that. So we're using this idea in this tower and cable situation where a technician installs the cables from a cell phone tower to the ground. To pass inspection, both cables must be the same length. Does this installation meet the cable length requirement? So if I look at the 2 triangles that were made by this tower and cable arrangement, I see that they both have a 52-degree angle right here. I see that they share a side. They share the tower as being the side of one of those triangles, so I know that side is congruent to itself. And then down here, I can see that I have a right angle on the left, and since I make a linear pair, I also must have a right angle on the right, giving me a congruent angle, side, and angle in the left triangle and in the right triangle. That, of course, means that the triangles are congruent by angle, side, angle. Since those triangles are congruent, I can take specific pieces and parts of them, like for in this case, the cable here and the cable on the right, and I can say, wait, those cables came from congruent triangles, so those cables must be congruent. Do you remember what that's called? That is CPCTC, corresponding parts of congruent triangles congruent shows the cables are the same. The cables are congruent. So once we know the triangles are congruent, we can say the cables are congruent. Moving on, going here, we're going to talk a little bit more about this arrangement, which triangles are congruent by angle, side, angle. When I look at the triangles and diagrams here, I see that both JK, that side, is included between the two angles that are congruent, and M is included between the angles that are congruent. But QR is not the included side between the angles that are congruent. So PQR is not congruent by angle, side, angle. It might be a congruent triangle, but specifically using the angle, side, angle strategy, we can't say that for sure. All we know is that triangle JKL is congruent to triangle. Let's name that second triangle. That second triangle will start with M, since M has one arc on it. Then it'll be N, because N has two arcs on it. And then O. That way we have all of our letters corresponding to all of the other letters. All right. Let's keep going. So here we've got this angle, angle, side idea. And this is another one that we already took a look at. It says, given triangle ABC, is the triangle determined by this arrangement, angle and side? Is it unique, right? Is this the only triangle that we could make with this angle, angle, side arrangement? And like we saw in that interactive tool earlier, it is the only triangle we can make. That's why angle, angle, side is a triangle congruence criteria. Because if a triangle has the same angle, and the same side as another triangle, we know they have to be exactly the same. So we can just say, yes, we've already covered that. Coming down here, we are using triangle congruence criteria to state whether each of these pairs of triangles is congruent. So when I look at this top pair, I look at the arrangement of our pieces here. I have an angle, a side, and an angle, a side, and an angle. So yes, that is angle, side, angle congruence. In the next pair of triangles, I've got 3 pairs of congruent sides, which makes that side, side, side congruence. Right? In the next pair, I have an angle with 2 arcs next to an angle with 1 arc, and the non-included side is congruent. The angle with 2 arcs, the angle with 1 arc, and the non-included side is congruent. And that one tells me that this is angle, angle, side congruence. And then finally, I've got a side, the included angle, and another side. Over here, I have a side, another side, and a non-included angle. So even though both of these triangles have 2 sides and an angle which are marked congruent, the position of the angle marked congruent is different. So they don't line up, and we cannot say that they are congruent by any of our congruence criteria. Once again, they might be congruent, but with the markings that are given to us, we can't say for sure one way or the other. All right, got a proof to do here. We want to prove that side FH with no markings is congruent to side JL with no markings. And of course, in all of our problems this chapter, we're kind of thinking, hey, if I'm making this proof, I'm probably going to need to show that these 2 triangles are congruent first. Then, once I know that, I can continue on to proving that a specific piece of those triangles is congruent. And you might already be understanding what theorem we might need to use for that. So we'll start our proof. We've got statements and reasons. They gave us a whole bunch of given information. So we'll take that whole bunch of given information and copy it into statement number 1. We know that GH is congruent to KL. We know that angle GFH is congruent to angle KJL, and we know that angle FGH is congruent to angle JKL, and of course all of that is given. With that given information that's already marked on the diagram, we see that these are in an angle-angle-side or side-angle-angle pattern. And since angle-angle-side or side-angle-angle is one of our congruency criteria, then we can say that these two triangles are congruent. Let's make sure we write their names right. So maybe one of them will be triangle HGF. And if that's the name of the first one, that next one needs to be corresponding, so that'll be triangle LKJ. And we know that they are congruent by the angle-side congruence postulate or congruence criteria. Since we know that those triangles are congruent, after we've proven that they are congruent, we can then go ahead and say we know that FH is going to be congruent to JL because of CPCTC, corresponding parts of congruent triangles are congruent. We know these triangles are congruent. We know FH and JL are corresponding parts, so we know that those parts are congruent by CPCTC. One last example here. What happens when we put our triangles together and use those together shapes and kind of talk about the congruence there? So we've got these quadrilaterals. It says all the sides and the angles of ABCD are congruent to the corresponding sides and angles of A prime, B prime, C prime, D prime. Are they congruent? And of course we can look at them and we can say, well, they look the same. And we can say, well, the sides and angles are the same. But since we don't have any quadrilateral congruence criteria, we can't say for sure that they're the same unless we can find another way to do it. We can't just look at them and say all the sides and angles are the same, they're congruent. I wish we could. That seems like it makes sense. We're going to need a more in-depth explanation. So when you look at these, obviously you can see that there is a dotted line in them that denotes them into two triangles. And when I look at triangle ABC, it has a side, an angle, and a side that are congruent to triangle ABC prime. So I can say for sure that triangle ABC is congruent to triangle A prime, B prime, C prime by side, angle, side. That's what's marked on there. Then I can do it again. I can look at the other triangle, ADC, and I can say triangle ADC. That's also congruent. That one's congruent to triangle A prime, D prime, C prime by side, angle, side. Those are the markings on those two triangles. And then there's a whole lot of math that we could explain that involves putting these two together. But since you can see that both of these quadrilaterals are made from the two triangles put together in the same way, we're going to generalize it way down. And we're going to say, hey, if I add the small angle BCA and the small angle DCA together, I'll get a bigger angle. And if I add BC or B prime, C prime, A prime, and D prime, C prime, A prime together, I'll get a bigger angle. And these two bigger angles, BCD and B prime, C prime, D prime, they'll be exactly the same. Do you remember what we use when we talk about two angles being put together to make a larger angle? We use the angle addition postulate. So that's what we're going to say here. Using the angle addition postulate, I know that A, B, C, D is congruent to A prime, B prime, C prime, D prime. Another way of saying that is if I take two pieces that I know for a fact to be congruent, like I do here, and I put them together in exactly the same way, like it's done here, then I will get two bigger shapes that must be congruent. And that's kind of what we did, just in less words. And of course, we can use this. This seems like a pretty simple problem, I'm sure. Given that the two polygons are congruent, what is the value of x? Well, we say, here's AD, that's 9. That's the corresponding side to EH, since these shapes are sort of turned upside down from one another and rotated. So all we need to do is say that 2x minus 3 equals 9, and we can solve that to find the value of, well, in this case, not m, x. So we will say plus 3, and we'll get 2x equals 12, divide by 2, and we get x equals 6, right? It's the only unknown there. M's are always just meters. So x equals 6 there. Easy problem. We'll have some like that on our work today as well, where we're using the idea of these two shapes being congruent to make some algebraic equations and solve them. Now tomorrow we're going to be putting everything all together, making some more proofs, some more formal proofs about two triangles being congruent using any of these triangle congruence criteria. And then we'll learn one more that is specific to right triangles. Right now you've just got your assignment to work on. If you've got any questions, make sure to ask. Have a good day.